Hello and welcome to the eTech podcast with me, your host, Ryan Morn. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. Really pleased to be here today with someone that I've known for a little while now. So Mihai Dorobantu from Eaton. Global corporation, heavily involved in vehicle electrification. And we've got a really interesting discussion coming up about efficiency, particularly in the commercial vehicle space. So welcome to the show, Mihai.
Thank you. It's good to be with you, Ryan.
Great. So could we just start by getting a bit of history on yourself, your background and where you're from and how you ended up doing what you're doing now?
Okay. Well, Ryan, I started with applied mathematics. I have a degree in differential equations, which was all nice and interesting, but what was more interesting was using that for modeling and simulation and coming in to solve real-life problems. So after about 3-4 years of doing modeling, simulation, methods for those, but also consulting with industrial partners in helping them set up difficult engineering problems, I moved into, let us say, the real industry. I worked for about 8 years with United Technology Corporations, where I've been mostly involved in their dynamic modeling and simulation groups, as well as controls and embedded systems. Working in diverse number of applications, like anything ranging from aerospace engine design to HVAC, air conditioning systems, vapor compression systems for air quality in homes. And then for the past 14 years, I've been with Eaton Corporation, starting really by setting up a capability in controls and embedded systems, but then have moved into our vehicle business, where I had the kind of the best job in the world to take care of advanced technology. And when I'm saying this is the best job in the world, it's because that's where you get to dream about new technology before it actually happens, and be at that fuzzy front end where you can experiment and where you can see concepts move into ideas, and then more concrete ideas, and then into new product design. So yes, that's who I am. Right now I'm responsible for technology strategy in Eaton's vehicle group and our interactions with government agencies such as regulatory agencies, which are really driving technology these days, as well as advanced R&D funding, which is, I think, how we got to meet a few years back.
Yeah, okay. And just so some people might not know, because, I mean, if you're in the commercial vehicle space, you probably know Eaton, but quite a lot of people might not know who Eaton are. And actually, even if you think you know who Eaton are, I'm constantly surprised, actually, by really what Eaton actually really does these days. So would it be possible just to get a little overview of what Eaton is all about as a business?
Sure, Ryan. So Eaton is a diversified industrial manufacturer. We are about a $22-23 billion a year in sales, to give you a sense of size.
Yeah.
And about 2/3, 60% of the company is really in electrical power management, electrical power distribution, power quality, anything ranging from switch gear from high voltage to medium voltage, substations, microgrids, data center electrical management. We do things like supplying electrical power for hospitals and stadiums and the like. So that is a big core competency of Eaton. The other 40% of Eaton is, we call it the industrial sector, which really has an aerospace power management division, a hydraulics power management division. So you'll see us on the John Deere and JCB and Case New Holland sort of mobile agriculture and construction type of equipment. And then last but not least, it's the vehicle group, the vehicle business that I work in, which is really the beginning of Eaton maybe 110 years ago. And we started by building axles for trucks and grew that business. Today, our vehicle business really has three legs. One of it, and people know us for different applications. So, for example, we are a large supplier of air management systems for internal combustion engines, such as valve actuation, variable valve actuation. Superchargers is what Eaton is known for, so boosting for internal combustion engines for performance, and these days for fuel economy, and even more importantly for thermal management for ultra-low NOx solutions. So that is one leg of our vehicle business. The second leg of our vehicle business is really torque management. So transmissions, especially for heavy-duty commercial vehicles, transmissions, clutches. We've been one of the pioneers of hybrid electrical transmissions or systems, if you wish, for commercial vehicles. We made that a business in 2007. And we are selling over 1,000 systems, commercial vehicle hybrid systems, a year for a very long time now. But we brag about having more than 2 billion hybrid electrical miles under our belt. And then the third leg of this business is our Immobility business, which really focuses on three things: power electronics. Yeah. So inverters, DC to DC converters, and chargers and the like. Power distribution and safety, we are number one in fuses, for example, contactors and power distribution units for both light duty and commercial vehicles. And then the third leg of that, which is probably where we interact most, is power systems for electrical vehicles. So multi-speed transmissions is kind of one example, but we also have 48-volt solutions and the like, where we are trying to manage power and torque for more efficient electrical vehicles.
Yeah, okay. And I mean, the combination of skills there within Eaton is really ideal. I can imagine sort of 10 years ago, people probably thinking, what are these guys doing? They do gearboxes and that kind of, are famous for that, but all this power electronics stuff, that's a terrible combination. What are they thinking? But it's right in the moment right now.
Yes, that's right. Other companies that look like us from the mechanical side have to go through mergers and acquisitions and joint ventures to be able to play in this space, Ryan. Yeah. We had to do our own internal M&A, if you wish, merger and acquisition, between our capabilities on the vehicle side, especially on the commercial vehicle side, in terms of managing power, but also and torque, but also understanding the applications, the commercial vehicle applications and their needs, and match that with the skills and the supply chain and the market position in power electronics and electrical power management, power distribution.
Yeah. Fantastic. So to get on into the kind of main topic, the kind of interest in terms of pulling this podcast episode together started out with seeing you talk about multi-speed transmissions, and it's a bit of an unusual topic, this, because obviously electric vehicles is a fairly new thing. So particularly in heavy duty, hybrid and electric has been around, but not really mainstream. But the kind of state of the art, so where most people are at, is EVs tend to have a single speed gearbox, so a much simpler gearbox than an internal combustion engine vehicle, and that single reduction gearbox drives the vehicle. But Eaton's got some really interesting technology, which is kind of the next step on potentially from this, and the kind of benefits and the experience in that was really interesting to me. So I wonder if you could just kind of talk on the experience that you've built up in multi-speed transmissions in heavy-duty applications.
Sure. I mean, this subject is near and dear to my heart. Look, as the pure electrical vehicles took off in the light duty, in the passenger car arena, it became very apparent that the electrical drivetrain is actually a simplification, if you wish, in terms of powertrain design. And not only that you go from an internal combustion engine with several thousands of moving parts to an electric motor that has very few moving parts, and yes, you will need a one gearbox, one-step gearbox for matching the electrical motor, much higher speed to what the wheels and the axle in the vehicle need.
Yeah.
But apart from that, just from the raw simplification of the mechanical complexity, there was also a significant simplification in controls. So suddenly all that quote-unquote black magic of calibrating multiple speeds or letting the human, the driver, kind of decide when to shift gears and for that, all that, I'll call it art and science, kind of went away and became a simple matching the throttle position, the accelerator pedal position to whatever the electric motor needs to be, which translates immediately to torque at the wheels.
Yep. Yeah.
And light duty, that was really good, and really, I think it was an important part of making it into light duty, into passenger cars.
Yeah, and of course the facilitator there is your electric motor has 100% torque from 0 RPM, and the torque tails off as the speed goes up, but the combustion engine has no torque at 0 RPM and has to develop torque as RPMs rise, and matching that torque speed characteristic of a combustion engine to what you need at the road is really difficult, whereas on an electric motor, you've instant torque, bang, away you go. So far so simple. Like, that's kind of
yes, right, and no doubt. But if you take a step back and you look at how much torque you need at high speed and at low speed, you find out that for passenger cars, for reasonable launch on a grade under reasonable weight conditions, the torque that you need at launch is, roughly speaking, the same order of magnitude as the torque that you're going to need on the freeway at high speed. It's maybe 2-3 times larger. So that means that if you have reasonable amount of torque accessed at very low speed, you can do all your low speed driving without needing a gearbox.
Yeah.
For commercial vehicles, the situation is very different. So commercial vehicles need an immense amount of torque at launch and at very low speed, compared to the torque that they need in order to put the power that they need to drive at high speed. So instead of the launch torque for a commercial vehicle can be 10-20 times the size of the torque at launch, can be 10-20 times the size of the torque that you might need at high speed. And that's a big difference.
Wow.
So, and what happened then with the first generation of commercial vehicles, pure EVs, this torque at launch was the deciding factor for sizing electromotors. And we ended up with really big electric motors.
Yeah.
So there are a number of variables that you have to look at. One is that in an electric vehicle, it is easier to make more power than it is to make more torque.
Yep.
If you need to make more power, all you need to do, and I'm having here some air quotes, because all you have to do is always a dangerous thing.
5-minute job.
But all you have to do is up the voltage, right?
Yes,
So up the voltage at the same current, you get more power. That's easy. Torque is different. Torque is really dependent on how much magnetic material you put in. So if you need to double the torque, you need to double your magnets, for example, if you are in the permanent magnet business, and that sort of becomes the limiting factor. So if you to double the torque, you really need to double the weight, you need to double the cost, you need to double the amount of magnetic material, the amount of copper that you're putting into the electric motor. So torque is expensive in an electric motor.
Yeah.
And you know that because your electrical motors are trying to get around that problem by making the axial flux motors are one way to limit this growth, this linear growth, if you wish, in torque. So you can produce a relatively high torque motor in a small envelope. But what happened in commercial vehicles, we ended up with these very large permanent magnet motors that were giving really unsatisfactory torque. So they were limiting the applications in terms of start torque.
Yep.
What worked very well for pass cars turned out to work not that well for commercial vehicles, for heavy-duty vehicles. And there's a limit to how much. So when you put a high torque motor, these, because they're so big, they also tend to be low speed motors. Yeah. So in order to achieve your road speed, 60 miles per hour or whatever it is, 90 kilometers an hour, 95 kilometers an hour for a commercial vehicle in Europe, there's only so much reduction that you can put in one gearbox before you start over speeding your motor at high road speed. So there's this sort of balance that has to happen between you want to put a deep reduction for startability to get that enormous torque, but you cannot put a too deep of a reduction because then you'll overspeed your motor, which, by the way, is also limited in speed because it's so big. You'll overspeed it at road speed. The compromise that people made was that they did EV commercial vehicles, especially the heavy ones, really just oriented towards flat terrain, not very high grade, because they cannot really solve that startability problem.
Yeah, and there's an acceptance that the EV would just never be quite as good as the conventional diesel. And I think actually that did damage the reputation of some EV programs. If you go back, I certainly heard feedback from end users who were complaining about the EVs not performing, and I always remember thinking that shouldn't be the case. We should actually be able to engineer a better EV solution than a diesel engine. But because of this big limitation and the trade-offs in motor size and current and the costs of these very large motors. It was always really difficult to get the performance to be comparable to that of a conventional heavy vehicle.
Right. And we ended up in a situation where I think electric cars were maybe 10, 15 years ago. I still remember the days when people would say, well, we'll never have electric cars because, just look at a golf cart. Can you imagine driving a golf cart on the freeway?
Yeah.
And boy, were people wrong then. But we still hear today, less so today, but 4 or 5 years ago, we heard the same story for commercial vehicles. Yeah, sure, it's nice to be electric, and there's zero emissions of any kind, the poisonous kind, of the global warming kind, zero emissions. This is all great, but it drives like a golf cart, and that had to change. That had to change.
Yeah.
So look, at the end of the day, there are three sort of myths. Here, misunderstandings around how electrical machines fit into commercial vehicles. The first one is that the higher torque at low speed will solve all the problems, as it did for most cases in pass cars. That's not true. So the second one is that electrical machines have a flat efficiency curve. And people like you are working to make it as flat as possible. But the reality is that there is an efficiency drop-off at the edges, both at the very low speed but also the very high speed of the electrical motors. And that means, for commercial vehicles at least, it means a huge efficiency penalty at high speeds. So you really do not want to drive a truck, a heavy truck at high speed outside of its most efficient spot. And those tend not to be at the high-speed end of the electrical motors.
Yeah, as compounded by the fact you tend to be lightly loaded at those higher speeds as well. So that's okay.
Right. So because just to put things into perspective, you are probably running 2 kilowatts per mile at high speed. That's just because of the aerodynamic loads and things like that. So it does make a difference if you're 80% or 90% or 95% efficient at those speeds. When you come from diesel land, it sounds, wow, what are you quibbling here? Because, we're between 80% and 90%, I would kill for that, because in a diesel engine, we're talking about, am I 40 or 45% efficient? And people will take a lot of trouble to make sure that, I'm not 45%, I'm actually 47% efficient at high speed.
Yeah.
Because of the penalty, we're talking about 10% difference on 2 kilowatts per mile, which essentially means 2 kilowatts per minute. And 10% of that adds up very quickly in terms of battery needs. So this flat efficiency, yes, it is there, and it is significantly better than what we're used to in diesel. But you still do not want to run your electrical motor at the high end, into the less efficient spot when you're at high speed.
Yeah.
And I think that the third piece, or the corollary, which people don't quite appreciate, of having high torque at low speed, is that you're power limited at low speed.
Yeah.
And, that power limited at low speed, you would say, well, in a commercial vehicle, who wants to drive like a maniac, right? Who needs, 500 horsepower at very low speed? You really don't. and that is true. that is true. You don't have to, to get to road speed in 10 seconds or whatever, which you could do by putting 4 or 5 high-performance pass car electric motors on a truck. And we've seen sort of concept trucks that do that, and they can unleash, 1,000 horsepower or something like that, and accelerate really, really fast. But the reality of commercial vehicles is you never need that, and you don't need that, and you don't need to pay the price in batteries and in electrical energy consumption for that kind of performance.
Yeah.
But there is one situation where you do want to have max power at low speed, and that is when you're braking. And this is completely different than internal combustion engines, where when you're braking or when you're coasting, you defuel the engine, and that's kind of the best you can do. But as you know, Ryan, for electrical vehicles, you can do much better than that, than no consumption while braking. You can actually regenerate. And when you regenerate electrical energy, even at low speed, you want to regenerate as much of it as possible. So being limited with a single-speed transmission, being limited at low speed in how much power you can generate, because then you're running the motor slowly, by definition, and you're in the high torque but low power mode, that then limits the amount of regen that you can do. And this is really where the magic of multi-speed transmission comes in.
So you get to keep the motor in its constant power, so peak power point, at its most efficient when you're doing regen, so you recover more energy back into the battery, which when you're slowing down a 40-ton truck is a lot of energy, potentially.
Right. So here's sort of what our experience has been. About 4 or 5 years ago, we introduced a 2-speed transmission for medium and heavy-duty buses, electric buses. And we did that mostly to achieve, so what did we achieve? We geared the truck so that in top gear, it will run efficiently at high speed. And then we put, for the start gear, we put enough reduction so that we could give, with a reasonable motor, we could give all the torque in the world that the truck, that bus needed for high-grade launches. And it turned out it was almost a 4 or 5 to 1 ratio. It's a big ratio.
Yeah.
It's a big change. So that means that at low speed, we could deliver to the wheels 4 or 5 times the torque rating of that motor. And together with what was happening in the axle, that was enough to give that bus or that truck enough performance to start on really steep grade while maintaining efficiency at high speed and while maintaining a relatively small motor. So the power of the motor was definitely given by, the acceleration requirements and the top speed, constant top speed requirements. That's where the power requirements came from. But the torque requirements were small because of that launch gear. And when I say small, it was about, I just said it, 4 or 5 times the reduction ratio. That means that the motor, from a torque perspective, could be 4 or 5 times smaller than what a direct drive would need. And that meant that the motor itself shrunk in size, in weight, about 4 times. Now, of course, you have to add the weight of the transmission. So at the end of the day, the powertrain shrunk by a factor of 2, but it shrunk by a factor of 4 in the expensive part, in the copper and the magnets and things like that. So that was pretty significant, while maintaining all the startability needs that these trucks and buses had, so that they could be deployed in any region, they could be deployed in any application, in the normal applications. We just removed that barrier. So that was great, and we launched these vehicles, and now they are kind of mainstay. And I'm pleased to say that by now, kind of the whole market has accepted that you need at least 2 gears in commercial vehicles. But then we asked ourselves the question, well, can we do better than that? And we developed a 4-speed transmission for the same application. And our initial thought was that what this 4-speed transmission will do will achieve 2 things. One, it will keep the motor, the electrical motor, more tightly into its maximum efficiency. These were motors that were over 90% efficient, and with 4 speeds, we could make sure that we were 90% efficient or better all the time, as opposed to 85% efficient or 80% efficient sometime. Okay? So that was the first piece. And the second piece was, if we have 4 gears, then we can shift more often, and the time to shift is going to be very short, essentially imperceptible to the passengers or to the driver. Right? Because we just made smaller jumps all the time, and the electric shifts are very fast because you use the electrical machine to synchronize the transmission. So we said we're going to go after 2 things: getting that last ounce of efficiency and improving the comfort in the truck. So the deepest gear remained the same. It was given by startability requirements on grade. The top gear was the same. It was to maximize efficiency at high speed, because that is the high power consumption mode. And the intermediate gears, their role were to make the shifts imperceptible, so to give you the ride quality and keep the motor longer in its peak efficiency mode. If we say we're going to eliminate some of those 85% efficiency situations and bump them up to 90-95% efficiency, we were expecting to see overall maybe a 5% improvement in efficiency, in electrical efficiency, which is not to scoff at, right? Because remember, these are commercial vehicles that are using over a day maybe 100, 200, 300 kilowatt hour batteries. So these are very large batteries. So saving 5% of that either in terms of range or in terms of battery, is a big deal.
Yeah.
And then we found out that in fact we were seeing 15, 20, 25% improvement in overall efficiency. And
sorry, just so 15 to 20, wow, that's incredible. So 3 or 4 times more.
That's a very big number.
Yeah.
That does not come from keeping that motor into the 90 to 95% efficiency part of the map all the time, as opposed to just some part of the time. So where did it come from? And then we start getting reports from the field. The foundation brakes in the 2-speed combination were being used for about 50% of the total brake energy.
Right.
And once we introduced the 4-speed, now that the time that the foundation brakes were used decreased so much that they were really used only for about 2% of the total brake energy.
2%?
So yes. Now, of course, this is drive cycle dependent. So these are buses that do a lot of braking, no doubt. And what's more important, they do a lot of braking at moderate to low speed. They don't really apply the brakes that hard at high speed.
Yeah.
You really don't want to be in that situation. No. But they do apply the brakes, they work the brakes hard at lower speed, and that's where the electrical machine was power limited.
Right.
So by running that motor, that electrical machine, I should call it generator in this mode, by running the generator at higher speeds because of the gearing, we were able to significantly increase, I would say even maximize, the amount of regen power.
Great.
So when you're talking 20% improvement in overall efficiency over bus routes, that starts to get people's attention.
Yeah, I mean, it's not so much the cost with an EV, is it? Because the fuel is so much cheaper than electric. Although I'm personally passionate about that efficiency, but it's more to do with the range. 15-20% extra range. That's less time charging. That's more utilization on the bus. That's more flexibility. I mean, even 20%, if you could reduce the mass of the battery by 20%, that would be hundreds of kilos if you didn't need the power. I mean, and that just becomes a very virtuous circle. Cost. Yeah, big cost saving on a smaller battery. Yeah, that's incredible. Yeah,
that's what drives the excitement here. And now we're taking this from buses to heavy-duty vehicles. In the United States, we have a significant problem in ports.
Yeah.
We have a lot of very old trucks that are idling or moving very slowly in ports, but then they have to be roadworthy and they have to move fast on freeways as they take goods from ports to distribution centers, to rail stations and things like that. That application is called dryage. Yeah. And it's particularly well suited for electrical vehicles, but these are heavy-duty electric vehicles. And they have, in California, there's a 7% bridge that they have to be able to make at reasonable highway speed, and they do work on the highway. They spend some time on the freeway, so they have to be efficient at high speed. But then they also have to do a lot of stop-start and a low-speed, low-load type of traffic inside the port itself.
Perfect for an electric truck.
Yeah. So we are helping some of our OEM customers there with 4-speed transmissions for these kind of applications that are significantly reducing the torque on the electric motors. Once again, there's nothing you can do. A transmission does nothing for power.
Yeah.
Power you have to build into the electrical machine and with the voltage of the electrical system.
Yeah.
That's given. But what the transmission does, it makes up for torque, and it allows you to access a high power mode during regen braking. And think about it, Ryan. When you accelerate a commercial vehicle, it's okay to use 30, 40, 50 seconds to go, from 0 to, say, 50 kilometers an hour or 60 kilometers an hour.
Yeah.
Nobody really expects these machines to be snappy.
No.
However, when you're braking from 50 to 60 kilometers an hour and you have to brake down to 0, many times you do not have 30 seconds or 40 seconds to do that, right? To absorb the amount of power that you put in. So it's much better to size your electrical machine and your batteries and your voltage for the power that you need for acceleration, knowing that you're going to need more of that power when you're braking, because you're braking at a faster rate than you accelerate. But then you can use gears to be efficient and to have access to that power while you're braking through gearings, rather than oversizing the electrical machine.
Wow. And I think it's such an alien concept to someone if you're used to designing internal combustion engine vehicles. You don't, it's not even a consideration. The thinking about using the transmission in that way for engine braking, it just doesn't. Diesel engines don't do engine braking really, unless it's such an alien concept. People would not be even thinking about that, and without having the experience of having done it, and as you said, even you guys were surprised at the level of improvement that you saw. Can I ask, it's all automated, so the transmission has its own control unit, it makes a decision about which gear it needs to be in and does it, or does the driver have to get involved at all?
So the transmissions that we build are all automated transmissions. I think that for the driver, it really feels like a single-speed transmission. There is no difference. The shift decisions are made based on the condition of the vehicle, so the torque request together with the mass of the vehicle and the efficiency map of the motor, which is really the motor, the inverter, the batteries, all these sort of energy considerations come in. And the reason why this is so snappy is because really the electrical machine is used to precisely synchronize the transmission. It would be very hard for a manual driver to actually synchronize an electrical transmission.
Right.
First of all, you don't have the audio cues of a roaring internal combustion engine to help you feel, so to speak, when you're at the right motor speed. And the reactions are just fast. I mean, we synchronize in typically around half a second during the shift. That is much faster than a driver can react with a sort of a manual command.
I mean, a lot of EV sort of, I was going to say aficionados or geeks, whichever your angle is. I definitely fall into the geek category. The original Tesla Roadster had a 2-speed gearbox, so they were using 2 gears, but they went away from that pretty quickly because they had some big reliability issues with it, I believe. It was essentially a modified internal combustion engine transmission. I know making gearboxes work properly with electric motors is a lot more difficult than people tend to realize from our own experience. So making this relatively complex transmission, I mean, it sounds easier in some ways than a gearbox to go with an engine, but there must have been some pretty significant challenges in terms of making that handle the torque in both directions and do everything that you need it to do.
That is correct, Ryan. Like everybody else, we took the natural approach, the incremental approach. Can we find an available transmission that we might modify and so forth to fit it for the EV situation?
Yeah.
We quickly found out that was not the way to go. So a number of major differences here. So you mentioned the first one. There's no need for a reverse. But not only that there's no need for a reverse, now you have to pay attention for your direct gears. How do they actually work in reverse?
Yeah.
So you start with a gear profile, which is now different because, high performance transmissions gears, the reverse gears have completely different geometry than the forward gears. So that is a change. The second important change here is how do you actually size the gears? So for an internal combustion engine, the deep reduction gears that are used for launch are perhaps sized for a few hours or maybe tens of hours of life.
Yeah.
And that is enough to last for 12 years, 15 years, whatever the life of the transmission is.
Yeah.
Because they're only used for a few seconds just at launch. Conversely, the high-speed gears are, they carry significantly less torque, so they need to be sized appropriately for life and efficiency at lighter torque situations. In the in the EV gearbox, these situations can be reversed, and the bus can well spend most of its time at in the first couple of gears, and spend a relatively small amount of time in its top gears only when it would be at almost highway speed or the high speed for whatever limited amount of time. All the rules of thumb, if you wish, or best practices in terms of gear sizing and gear life and things like that kind of get thrown out the window, and you really have to take a clean sheet approach and go back to the fundamentals of why we size gears the way we do and things like that, and relearn, if you wish, reprogram our DNA almost when we think about EV transmissions. Otherwise, we just inherit the limitations of the transmissions. Even the third piece of this is what the power plant is doing. So, you have high torque, low speed electrical motor. You have low torque at low speed in a diesel engine. You have a relatively flat maximum power, rated power area for the electric motor. For diesel, your power starts dropping at higher engine speed. The transmission design actually reflects those characteristics. And I think the last piece here is really how you actually synchronize the transmissions. The fact that the electric motor is so controllable, so much more controllable than an internal combustion engine, offers new opportunities for very fast synchronization, very precise synchronization, while eliminating things like synchronizers and clutches and things like that are always sort of life-limiting and performance-limiting parts in a conventional transmission.
Wow. One of the things that we often hear people struggling with on EV programs, and this is OEM programs as well, is the noise. So because transmission noise, because normally a normal transmission has an engine to run against, which is pretty noisy. So the transmission you don't really notice, but in an EV, because the motor is silent, you all of a sudden transmission noise starts to become a major challenge. And we've heard some stories from some really big OEMs getting caught out by this. On a commercial vehicle, was noise a consideration? Did you have any work to do there, or did it all just come together okay?
Well, the answer is yes. Noise is a consideration. We had some experience with that from the past. So, as we developed hybrid transmissions, we faced the problem with our commercial vehicle hybrids for a long time. Especially when they launch electrically, or when they are in pretty much driven by the electrical motor only, so that the diesel engine is either idling or perhaps even turned off. So yes, noise is an issue, but in the commercial vehicle space, we've been dealing with that issue for a long time. The reality is also that noise, even for internal combustion engine transmissions, for conventional transmissions, noise has been going down more and more as the customer expectation has been going up in terms of driver comfort and so forth. So even though during snap accelerations or at very high speed, the transmission noise is hidden by the engine noise, at lower speeds, under lighter load consideration, the transmission noises today is significantly less than it was 10 years ago, let me put it that way.
Right. Oh, fantastic. Was there anything special needed for lubrication? Again, I've seen that cause a lot of issues with the low-speed torque, basically welding gears up in poorly designed gearboxes. So, transmission lubrication seems to be a big topic on electric vehicles. Do you have any special features for that?
Well, I mean, Eaton is a transmission manufacturer for very many years.
Yeah.
So I think we have evolved a lot, even on conventional transmissions, from many gallons of oil and that was being splashed around by the gears themselves, sort of being dipped into a bath of oil. We've moved to precision lubrication now for efficiency reasons, and that's what we're applying also for these transmissions. At the end of the day, so-called dry sump approach is really the way to go about lubrication, because it allows you to control lubrication and to do it in an economical fashion. At the end of the day, having a big oil bath in which the gears turn around, that's also an efficiency hit. Yeah. So we have moved to precision lubrication with our conventional transmissions as well. And what that means for EV transmissions, what may be different for EV transmissions, is the need to have some kind of lubrication pumps that are driven, well, obviously electrically, maybe driven independent of the transmission itself. Yeah. Most of our normal line haul diesel transmissions, the oil pumps are driven by the gears themselves. That is not the case with the EV transmission. They do have their own lubrication circuit. So I think the answer, Ryan, is yes, we do pay a lot of attention to lubrication, not just for the sake of lubrication, but also for the sake of maintaining that high efficiency, so that we don't waste away all the efficiency savings by running the motor better or the electrical machine better, and then we waste it away by not being careful with lubrication.
Because of course, that is one of the criticisms when you hear people talking about what good single-speed transmissions in EVs, multi-speed. People talk about the extra drag in the gearbox and that the oil churning losses and such like. But obviously, the system that you guys have developed completely gets rid of that because of the precision lubrication and the dry sump technology. So it's I think it just goes to show with that extra bit of experience that you've had and the all of the road miles that you've managed to accumulate, that you can really develop a good product.
Yep.
So just noticing the time, there's so many questions that I could ask, but we probably need to think about wrapping up. Could you give me a comment in terms of what you see, somewhat with all your experience and in the space, where you see the next couple of years going? What's exciting you at the moment in terms of technology coming through and in the field of electrification? What any kind of predictions that you have?
Well, I think there's still an interesting play going on between centerline transmissions, like the ones that we have, where we can put more gears, and we're finding out that four gears will maximize that performance, especially during brake, and it will also feel very smooth, so imperceptible for the driver. And we also like the center location, thinking that in commercial vehicles is a high mix, low volume type of market, and we still think that the internal combustion engine is still going to be there for a while. So the centerline transmission has one additional advantage, that it is in some sense modular for the chassis. You can build the same chassis with a internal combustion engine or with an electric motor. Yeah. Not everybody's going to do that, but in the high mix, low volume type of applications, having that kind of modularity so that you can quote unquote swap internal combustion engine for electrical drive does have some advantages. On the other hand, we are watching the rise of the e-axle, the electrical axle, or the wheel hub motors, or something that's approaching individual wheel motors. And there are certainly advantages to that architecture as well, especially in things like buses or city delivery vehicles where floor space is really important. So I think as we go into the future, as we look into the future, the market will likely start bifurcating into more sort of general purpose applications where modularity, even with the internal combustion engine, is important at the chassis level, versus specialized applications or those where floor space is critical that will probably go towards the e-axle or variants or dialects, if you wish, of those. So centerline transmission versus the transmission being incorporated together with the motors into the axle itself. I think that is a big bifurcation that is probably going to happen, especially because on the e-axle side, two-speed e-axle is probably the higher level of complexity that you can afford without sacrificing the differentiator, which is floor space.
Yeah.
So I think that as far as transmission goes, we'll see evolutions in both directions and applications in both directions. And I think it would be unrealistic to say, well, one is going to win and the other one is going to go away. I don't know that anybody can make that bet. So probably the wise thing to do is to hedge your bets against both architectures. I think also on the theme of low volume, high mix type of market, I think the electrical network, if you wish, on trucks will have to be flexible so that it can be easily reconfigured with minimal non-recurring engineering costs, with minimal sort of capital investment to adapt from one type of electric vehicle to another. So to that aspect, we see flexible high voltage distribution boxes where you might have a modular sort of power electronics and power distribution, contactors, fuses, and things like that can be almost plug and play, so you can add as many accessories or power levels of accessories as you need in one box that is thermally managed and EMC insulated and so forth. So I see that flexibility need just because of the nature of the market. I think that also we're going to see a change in accessories as the conventional diesels will need more and more electrical accessories for to lower their carbon footprint and to lower their NOx emissions. So we're seeing a need for higher power electrical heaters, for after treatment, for more efficient after treatment to reduce NOx, especially in cities. We are seeing the need for electrical air conditioning and electrical accessories to reduce the accessory load. So these electrified accessories in the mass market, I think they'll have their implication for commercial electrical vehicles as well. And people are now talking about a 3-voltage architecture where on the high voltage you only do traction inverter and batteries and the traction part and maybe some high power electrical accessories that are truly much more efficient at high voltage than at lower voltage, and then a simple DC to DC converter, and then suddenly you are on a 48 volt accessory bus that might be common with the internal combustion engines, and that will drive lower costs on everything else but the batteries and the motors without sacrificing in any meaningful way efficiency.
Yeah.
I think these are the trends to watch for in commercial electrical vehicles.
Brilliant. Well, fantastic. I think thank you so much for taking the time out to do that. That was, I've learned so much. It's fascinating. So thank you very much for that, Mihai.
Yeah. Well, thank you, Ryan. It's been a pleasure. You are making me talk about things that I'm very passionate about.
I can tell, yeah.
And I think the market is just about starting to realize the potential of the technology and the fact that the costs aren't really perhaps as prohibitive as we once thought. So.
Yeah. I certainly, I 100% agree there, and hope so, given the nature of my day job as well. So we see that too. Just when you think it can't change any faster, it seems to pick up yet another gear. So if you pardon the pun. So,
There you go.
Good. All right.
No, it's truly exciting, and thank you for the opportunity. I really enjoyed the conversation and the very thoughtful questions that really probe hard at the heart of the matter.
Brilliant. Wow. Well, that was amazing. So massive thanks to Mihai for taking the time out to talk to me. I've learned so much from that. I hope that everyone else has as well. Don't forget to leave us a comment and a rating depending on which platform you're listening to us on, or hit like. Of course, subscribe to our channel. If you go across to YouTube, there's some great video content over there as well. So if you're interested in some electric vehicle technology videos, you'll find those on our YouTube channel as well, all of which can be accessed through our website. And don't forget that as well, if you have a question or a query or something that you'd like us to talk on in some more detail, maybe this podcast got you thinking about something, or a previous podcast that we've done, send your questions in to us, and we'll tackle those as we can through the podcast episodes. Okay, that's all we've got time for today. Thank you so much for taking the time to listen to us, and I look forward to speaking to you again soon.